last thing, what is the last thing? Damp-driven oscillator, in your notes. And we've been doing that in mechanics, but Lee, you've seen this before too, right?
Yeah.
Damp-driven oscillator. So what we're gonna do is just look at the whole problem in terms of Fourier integrals. So the damped-driven oscillator, we can start with this differential equation. F of m, and that f of t was going to be f naught, so f naught cos capital omega t, because we need the other omega. So that's the driving frequency. And we want to treat this problem using the Fourier expression. So x of t would be this integral of the Fourier transform x hat omega e to the I omega t d omega. Okay, so that would be the function that we're looking for, but of course it's a differential equation, we don't have it yet. And our x hat of omega would be equal to 1 over root 2 pi minus infinity to plus infinity x of t e to the minus I omega t dt. So how do we go about this? This is going to be a multi-stage problem. The first thing is we have on the right side here a function of t. So we just have to, and this one is given, so we need the Fourier transform of this function here. I'm going to put the alternate, not the alternate, but the other formulas here. So in general, just as we have x of t here, we have f of t. I'm just going to rewrite these. 1 over root 2 pi f hat of omega I omega t omega and f hat of omega 1 over root 2 pi minus infinity to plus infinity f of t. Same thing, okay, I've just written things down twice. But if we want to solve this using Fourier methods, we have to get this function here first. So this one is given, and we can know everything about it, Fourier transform and so forth, except that this function is not vanishing at infinity. Okay. So one of the requirements here is that the Fourier transform and the function itself vanish at plus or minus infinity and vanish sufficiently strongly. So I'd say the first step of this discussion is because cos omega t does not vanish at infinity, we have to multiply it by what's called a convergent factor. T goes to infinity, what we'll do is we'll consider cos omega t e to the minus alpha t. In fact, let's this here was for t greater than or equal to 0. Follows the time. Yeah, so the first thing we're going to do is consider, rewrite this, consider f of t equals f naught cos omega t e to the minus alpha t, where t greater than or equal to 0, and and the force is 0 for t less than 0. So that's the first thing. And what does this look like now? T f of t, well, it's 0 here, and then it's something damped, it's e to the minus alpha t. But what we can do is solve the problem with this damped oscillator, and then in the final result, we can let alpha go to 0. We'll just get the result for, we'll get the result that we started out asking for here. So this is an important little device here. We're using this as a converging factor. Convergence factor. After the calculation, let alpha go to 0 in our result. Good, so now our task is to find the Fourier transform of this function. And I think we did that on our exam with different letters. Okay. So let's go ahead and look at that again. So now, we would say f hat of omega 1 over root 2 pi minus infinity plus infinity of this thing. Actually, because we've got that 0 there, we're just going to go 0 to infinity. Okay, 0 to infinity. F naught goes omega t. But now we've got that e to the minus alpha t. E to the minus I omega t. t. So let's see how much of this we have to do. 1 over root 2 pi. F naught. And we're going to use the cosine formulation, 0 to infinity of 1/2 e to the I omega t plus e to the minus I omega t e to the minus alpha t e to the minus I lowercase omega t dt. So we would have f naught root 2 pi, have 2 there as well. And we're going to put these all into that same exponential. So e to the I omega minus alpha minus I omega t plus e to the minus I omega minus alpha minus I omega t dt. So we got to evaluate that. So we get f naught 2 root 2 pi. And we're gonna do these integrations here, and for t goes to infinity, the e to the minus alpha t is what makes it be 0. So the both upper bounds are going to be 0, and at the lower bound it's going to be e to the 0, which is just 1. So for that reason, you would have 1 over I omega minus alpha minus I omega. And since it was the lower bound, we've got lower bound also minus one. Okay. So that's our Fourier transform. We could kind of declare victory, but we want to put it into a standard form. Okay. What we want this denominator to look like, what we want this factor here to look like is, if we factor out minus I, we have minus omega minus I alpha plus I alpha. Plus omega. So minus I plus I omega. And more to the point, we actually want this to be minus I times omega minus I alpha plus omega. And we want this one to be minus I omega minus negative omega plus I alpha. Because this is the standard form in which we do these things. So we'll have f naught over 2 root 2 root 2 pi. And down here we'll have, keep the minus I for the moment, omega minus plus omega, omega minus negative alpha plus. Okay, and then in the numerator, we have to clean this up. We've got I omega plus alpha plus I omega. And then on this side, minus I omega plus alpha minus I omega plus I omega. How's this gonna clean up? We're gonna have 2 alpha. Oops. Okay, we're gonna have 2 alpha here. These two are gonna go away. Plus 2 I omega. Okay. Okay.
Do we take alpha goes to 0?
Not yet, that's a good question. So we're not ready to take alpha goes to 0 yet. In fact, we have to inspect this thing in the complex plane. Good, so I'm just gonna leave it like this. So we'll have top and bottom by I. Get rid of this one, and then I'll have minus sign, so I'll have 2 I alpha minus 2 omega. For the moment, okay, this is fine. So what we want to do is study the structure of what we have here now. In fact, I'll put it in the same form, so omega plus I alpha we've done this calculating, we have to see where this thing lives in the complex plane. So this was our f hat of omega. This thing right there. And in particular, since we're doing contour integration, we see there are poles here in the complex plane. That's why I factored this out here. So this is omega, you can say this is omega minus omega 1 times omega minus omega 2, and then these omega 1 and omega 2 would be the poles of this thing in the complex plane. So let's see, we don't have so much board space. Yeah. So I'm just gonna put this up top and then continue on. Okay, so f hat of omega 1/2 √2 pi. Really interested in is the denominator here. Close parentheses. Omega minus omega plus I alpha. Okay, so now I've got some space freed up. So if we were to plug this, back into this formula, we should get back our original function. Okay? But suppose you're looking in the complex plane here, and here is a Fourier transform. You want to get your original function back. Then your complex plane is the omega plane, complex omega. So where are these two poles located? The places where the denominator vanishes, where are they in the picture here? This was a positive real frequency, right, from our cosine. And alpha was positive because we needed even minus alpha t for the converging factor. So where are those poles located in the picture? I'll give you a hint. They're in the upper quadrants, right? So you can say, okay, I'm gonna go over, for this one, I'm gonna go over to omega, and I'm gonna go to plus I alpha. So there's where one of those poles is. And the other one is with the minus omega, so it's over here. Minus omega. So we've got two poles there safely there if we want to do a contour integral. Say we wanted to do this type of integral along the entire real axis. You would close it around the top, and then Jordan's lemma would tell us that for positive t it vanishes. Okay. For positive t, the semicircle vanishes as the size goes out to infinity. So that is the result we're going to hold on to. And you can check the arithmetic there, make sure nothing went wrong. Okay, so that's the right side of this differential equation that we're interested in. So what you can say is, for the right side of this differential equation, I have this presentation, I have that out of omega, I have that t. Right side, it's all as well because of the converging factor. This one we will take to zero later on at the end, but not yet. We need it there to do integrations. So now let's go to the differential equation, and we're going to set it up this way. We're going to the left side, we're going to take the x of t and take two derivatives. So now for this equation here, so right now, for differential equation, we have the left side, 1 over root 2 pi. What we do is we take this x of t here and start taking derivatives of it. So if you had that x of t, minus infinity to plus infinity, and you had the x hat of omega, we don't have it yet, but since this is the x of t, the two derivatives, two time derivatives, just bring down I omega squared. So that's why we have I omega squared. Then plus 2 gamma times the first time derivative, we have plus 2 gamma times I omega. And then for the third term on the left side, it's just a multiplication plus omega naught squared. E to the I omega t. D omega. Right? So that's the left side of this differential equation. The right side is integral, so 1 over root 2 pi, integral minus infinity to plus infinity, f, I'll use capital F hat of omega e to the I of omega t d omega. This one is known. We just calculated it. So F hat of omega is known, but you see how I set the equation up? I just did a Fourier integral on both sides. So if this is the case, then x hat of omega times this, so everything over the red bracket there must be equal to f hat of omega. Because everything otherwise is the same, right? Integral 1 over root 2 pi, integral e to the omega t d omega, same on the left side. And so what this does is it gives us a way to find the missing x hat of omega. Because if this left red side is equal to the right one, we can say that x hat of omega is equal to f hat of omega divided by this I omega squared 2 gamma I omega plus omega naught squared. And since this is already known, and this is just something that we'll work on a bit, you could say now x hat of omega is known, and we can go back into this equation and have our solution. So there's a lot going on here, and one thing we want to do is factor this thing. So let's work on this a little bit, since we already have everything up here, and then we'll put this giant result up there. So what we have is minus omega squared plus I 2 gamma omega plus omega naught squared. And we'll do omega squared minus I 2 gamma omega minus omega naught squared equals 0, so we'll have a minus sign here. And then we factored this thing before, but let's just write this out. We'll have omega equals 1/2 to times 2 gamma plus minus square root of e squared negative 4 damp case, so gamma is small enough. Okay, don't worry about that. And what we can now do is write this denominator in the same form we did before. So equals be right there. That's one here, I can sneak that into here. So we've got equals f of omega. What we want is, I've got that minus one, so put a minus one up here. We want omega minus one of these omegas, so omega minus I, oh, the two was gone. Minus I gamma minus root omega naught squared minus gamma squared times omega minus I gamma plus root omega naught squared minus gamma squared. So up to a stray minus sign or two, I think we're in good shape here. What we're gonna do is we're gonna write this whole grand monstrosity up on the board and then analyze it. So we wanna make sure everything's reasonably clear here. Because there are gonna be 4 poles on the board, and we just wanna see what they're all doing physically. So let's go show minus. I think I got that. Yeah. Okay, so we have this. Now I'm gonna clear up some space over here. I'll just showcase this thing. Or I'll put it up here just so it's space. X hat omega. So what is this X hat of omega? We wanna write the whole thing down. So X hat of omega is this one with the addition of these 2 poles there. Let's see. So right under here we'll write X hat of omega, and then we'll start to analyze. So the F hat of omega, a minus sign, absorb that minus sign here. You can cancel the 2's, looks like we can do. So we'll have F naught omega minus I alpha. We'll have root 2 pi. Here we go. So let's make these as clear as we can. I'm gonna write out all 4 of these. I'm gonna write out all 4 of these. So omega minus omega plus I alpha. Omega minus negative omega plus I alpha. And then these 2 that we just gave here. Omega minus I gamma minus root omega naught squared minus gamma squared. And last but not least, omega minus gamma plus root omega naught squared minus gamma squared. Good. Let's stand back here and admire handiwork. live in the complex plane?
Four poles.
Pardon?
There's four poles, right?
Exactly, there's 4 poles. I can use this piece of board. So if we go into this integral and get this grand result, it's really going to be a question of evaluating 4 poles, and this is the omega plane. It's either the I omega t, t's positive, actually t's t is negative infinity to plus infinity. For positive t, we would circle the top half. For negative t, the bottom half. Let's go ahead and put these poles in first. So we have, I'll put this here, negative omega, and I've got I'm gonna put the I alpha here for special reasons. Okay, so we've got this pole, we've got omega, I alpha. So those are 2 of those poles. What about these 2 here? Now gamma I'm not letting go to 0 later on. So I'm gonna just put it up here. So we've got gamma minus omega naught squared minus gamma. So I gamma. So this other one, I'll call this I gamma. Okay, and this was the natural frequency of the oscillator's driving frequency. These 2 cross. So we have 4 poles. And the point is that just knowing these poles and interpreting what they do is going to tell us about this problem without having to go in and actually necessarily solve it. Okay? That's the point here. So for example, these 2 poles from the driving force, right? Those are the ones we're going to let alpha go to 0 when we're done. Okay. These 2 are from the actual damping of the oscillator. We're not letting gamma go to 0 because that's the actual damping of the oscillator. So this alpha, this I alpha here is the one that we're going to let go to 0. Okay, now suppose you have to throw this thing into here. What you're really looking for, or what you're really looking at, is some constant. I'm going to use A. Yeah, you've got some constant omega minus I alpha, and you can say you've got an omega minus omega 1, omega minus omega 2, omega 3, omega minus omega 4. And that's the structure of what we're looking at. So if you look at it in this form, it already looks better than this. What if you had to do this integration to get x of t for positive t? So for positive t, here's your contour. Okay. This is x of t greater than 0. So when t is greater than 0, you needed the upper half plane because Jordan's lemma gives you convergence for e to the IC, right? Positive. For negative t, you actually have to go this way. Okay, let R go to infinity. For negative t, notice you have no poles. So because you're circling something with no poles, you get an identical 0, which is what we started with this problem, right? We started with the no driving force, so identically equal to 0. Okay, so this is Jordan's lemma. I'll just write here Jordan, that's where this comes in. And for x, t less than 0, you're doing this curve here, this contour. And it's also because of Jordan's lemma. Okay, so who remembers what we did with the transient on the damp-driven oscillator in mechanics? Remember remembered the solution to the damp-driven oscillator had a transient, and it had the remaining term, the inhomogeneous solution. So I'm going to put a note here as well with regards to the transient. The transient was these two poles. So, you know, this integral has 4 poles to evaluate. Got to go around there, pick off 4 poles. But these two are going to vanish as t goes to infinity anyway. So we could ignore those if we're not interested in finite times. And that would mean that the damp-driven oscillator for, you know, t goes to infinity would only involve these 2 poles. So we would evaluate only 2 of those 4 poles and declare victory on that. Okay. Evaluate 2 of the poles. Since I'm naming them, I would call this, you know, this would be my omega 1, omega 2, omega 3, and omega 4. So if we don't need transient, we just evaluate these 2 poles and then let alpha go to 0. So I wonder if we could assign that. I'll just put that down as a note for starters. So. Actually, before we do that, let me erase some of this here. We gotta leave this all on one board. Okay. Suppose you're using the residue theorem now. What is the x of t? Say t greater than 0. It's going to be, you've got that 1 over root 2 pi, and then it's going to be 2 pi I sum of all the residues of, you know, x hat of omega equals omega k equals 1 to 4. Okay. So that's the first thing. Okay. And the residues are just the evaluation of this whole thing. Is a monster, but it's just the evaluation of those. So you've got 4 residues to evaluate. 1, 2, 3, and 4. Good. Let's declare victory right there. What would these residues look like, though? You're just going to get a bunch of constants here when you do these out. Constants here. The time dependence is going to be up here. So you're going to have something like e to the I omega 1 times t and so forth, right? So you're going to have something like, you got to do this step by step. 2 pi, you're going to have 2 pi I, and then you're going to have something sub k e to the I omega kt, k equals 1 to 4. Because, right, you're just evaluating those things. You're just getting a bunch of, you know, constants with all this material there, but the time dependence is up there. So what is e to the I omega 1 t equal to? Just to show you how this all unfolds. That's e to the I. My omega 1 was this one, so that's minus gamma plus I alpha t. Right? E to the I, you know what, let's do this. E to the I omega 1t plus e to the I omega 2 times t. Because then I've got this one plus e to the I omega plus I alpha t. And I times I is negative, so that's going to be common on both of those. So what you actually have is e to the I, I'll do this one first, omega t plus e to the minus I omega t e to the minus alpha t. Right? But we didn't calculate this stuff, and you know, remember we did the amplitude of the Rubin oscillator? Bit complicated, so that's what we're going to generate here. Yeah, but who recognizes this? This is 2 times the cosine of omega t. 2 cos omega t e to the minus alpha t. So now at this stage we can let alpha go to 0. And this is that driving result. And all this stuff we haven't calculated is that amplitude information and the phase information that would be in there as well. But that's how it'll come into play. And if you only need these two because you say the other two are going to die away anyway, the other two are going to go away because they are the transient. Because the same thing's going to happen with the I gamma. You're going to have it e to the minus gamma t, and that's the one that goes away as a transient. This is the one that remains. So the point of this exercise is to just see everything that's going on before you actually do more of the calculation. When you evaluate, by the way, you have to evaluate all of these denominators, except for the one that you're canceling with the residue theorem. You have to evaluate them at the relevant omega there. So that's where these complicated constants come into play. Time dependence just came out exactly like that. The other two will give you the transient. And that's where I'm going to leave this problem. Okay? What I want to do is assign a simpler one, we'll come up with a simpler one, namely a first order differential equation where we can test this process out and it's much more oversight. This isn't bad, but there's too much of it going on. You guys see what's going on here though? Right? We were doing the residue theorem and just picking off these 4 residues. I just picked off 2 of them in terms of their time dependence. And so we'll come up with a simpler version, first order differential equation where we can really get in there and understand it easily. But from the point of view of physics, this is a lot of physics. You can say, for example, suppose gamma is large. What does it mean for gamma to be large in a damped oscillator? Large damping, right? Large friction. So what you see as large friction means that these poles get ever larger. Okay? Small friction is if they go to 0. So the point here is the position of these poles in the complex plane describes the physics for us. Once we know the same with these alphas, right? The alpha goes to 0, then you have no damping at all. The alpha gets larger with strong damping. And as far as these omegas, larger frequencies are out here, smaller frequencies are closer in there. So anyway, this picture here should add a lot of meaning once we get more practice with these things. We've got our integral, we got our integrals, and the residue theorem says, we're just replacing the whole thing with those, and so forth. Okay. But when we get back to the homework, we'll be doing the simpler versions of this. I just wanted to show you the whole application. Good, so that's a major application. Let me see, I had some other major application I wanted to get started on. Couldn't finish that today. One of these books here. Yeah, I have a couple of versions of this. Yeah, this one's good. Erase all this. Everybody got this? This was important here. These were the two, yeah, so just, this was the K equals 1. And this was the K equals 2. Of that whole thing. Okay. Okay, this next application takes us to thermal physics. Who remembers thermal physics?
Define thermal physics, please.
Specific heat.
Yes, vaguely from 4B.
Good, exactly. So that's what I'm gonna go into the material we have for, in 4B. And then derive a differential equation of heat and solve it using the Fourier techniques as well. So this solution does not use the residue theorem, but this is a longer process here, so we'll just get started on this. We're in no rush. Heat transfer by conduction. Who remembers heat transfer by conduction?
Equation for it.
There's an equation for it, exactly. Let's see what else we're going to use. Gauss's theorem, yeah, we have some good stuff. What we're trying to do is derive the differential equation of heat or diffusion. So that wouldn't have been in physics 4B, so we're gonna start with what was in physics 4B. So just to characterize this application, we are doing the heat equation. We'll just call it the heat equation. So I want to be reasonably thorough on this, okay? So we're in no hurry. So from physics 4B, we'll begin with the specific heat. Letter C, and the formula we're going to use is Q equals MC delta T for thermal energy entering or leaving a body, okay? Thermal energy entering or leaving a body. Yes, since we haven't seen this necessarily for a while, we're in no hurry. This is a good result here. So we have that, and the second thing we have is heat transfer by conduction. And again, I'll use the 4B formula. And here we'll have dq dt. I'm going to do the magnitude. It has a direction. K, A, delta T, delta L. And the picture here was that you had some barrier, some conducting material of area A, and you had, you had a delta T, I'll put TH and TC. So if I have a higher temperature on the left, then the energy is going to flow through it, and the delta L is the thickness and the area right there. And K is then the coefficient of thermal conductivity. And since this is energy over time, this is a power. Yeah, so I'll just say power, energy flows from H to, flows, energy flows from TH to TC. Flows TH to TC. So that's the picture. We have specific heat transfer by conduction. Good. Now what we're gonna do is let Q equal energy flux unit area. So this is flux, energy unit area, and time. Actually, dimensionally, I just have energy unit area and time. So this is energy per time. I would take out the unit area. You can see I'm just left with K dt over dl. So I have Q equals minus K gradient of the temperature. So this takes care of the dimensions. And the direction of the energy flow is going to have that minus sign because it's the gradient of the temperature. So if this were just the x direction, we'd have dt over dx, but since it's in three dimensions, it's the gradient of the temperature. Good. Gauss's integral theorem. So we're going to have through an area Q dot n hat. N hat is an outer surface normal. So this is the air. This is the energy flowing out of the volume. Okay, energy flowing out of the volume. Outer surface normal, so if it's flowing out, this is positive. If it's flowing out, however, the energy inside that volume is diminishing. So we have to put a minus sign in by hand, energy in the volume. So it's diminishing in time, so flowing out equals minus d over dt integral rho c t d volume. So that's the thermal energy. So mass per volume line CT. Good. So that's dimensionally correct. And now we're going to, since it's still volume, we're going to use Gauss's integral theorem to turn them both into volume. So this one here is integral volume Q dot n at dA, yes, divergence of Q d volume by Gauss's integral theorem. So you change a surface integral into a volume integral, taking the derivative of that vector. And now we can compare these two, because we now have two volume integrals. So comparing these two, we're bringing them both under one integral. is what we'll do now. So now we have under volume, we have divergence of Q plus d over dt rho c e. D volume equals 0. D volume equals 0. And by the standard argument that this is just an arbitrarily chosen volume in space, we let the integrand vanish. Okay, so now it's all there. So equals 0 because arbitrary volume, arbitrary. And now what do we have? So we have right up here, perfect timing. So we have d over dt rho c temperature equals minus convergence q, right? But q is minus k gradient t. And we can do this. Rho c, the temperature with respect to time is equal to k divergence gradient t. And that's one of the differential equations of mathematical physics. We would, we would bring these constants over to the right side, which we'll do, and then write down our final result. We'll do right here in red. So here's what we've arrived at. D temperature with respect to time is equal to alpha del squared T. My alpha is just K over rho times C. My del squared is div grad. So everything's up there. How much of that are you guys familiar with?
I don't think I've seen the divergence before.
Okay, good. We'll take these step by step. Oh, so you haven't seen the Gauss's integral theorem?
Maybe.
Maybe not. But anyway, I take it on myself to explain.
A lot of this stuff turns up in like 1 unit, and then you don't see it again for a year.
Exactly. And in calculus, you barely see it, but in physics, we'll see them a lot. Okay. So we'll do actual sections on all these things, integral theorems and everything. Integral theorems are really interesting and fun. Okay, but let's just tie all this together, and then we'll make a little list of the things we have to know. So what we did was we took the basic specific heat and heat transfer equations, and we turned them into differential equations themselves. Okay. And then we were able to combine the two differential equations via Gauss's integral theorem, and then we got to this heat equation, which is also a diffusion equation, so it plays a big role in mathematical physics, the heat equation, or diffusion equation. And let's make a little, since I'm glad these came up, these issues came up, because we make a little list of things that we are going to have to cover. So we need, the first thing is divergence, gradient, and while we're at it, curl. So divergence of a vector, gradient of a scalar, curl of a vector. So that's something we'll study. And then what we had was divergence of the gradient, so del squared phi is actually rad phi, with divergence of the gradient, so we're gonna have to make sure we write about that. These are all great subjects, by the way. And then integral theorems. Integral theorems, Gauss and Stokes, names come to mind. I'll just write Gauss, Stokes, etc. Good. Now, how about you, Eric? How are those names? All that terminology.
I heard of the strokes and Gaussian.
Gauss, yeah. Haven't used them much
No.
recently, yeah. We talk about them a lot in physics, so you'll, 107 A and B's, whole reams of stuff. And the rest of you guys can always stand the review, right? Do you no harm. Good? So I'll come up with an order of discussion here. You know, we'll explain this more, do this problem, and then we'll make sure we circle back to this stuff here. We could do it in 105A or this class or both, actually, that'll be good. Okay, looking forward to that. That's all we've got for today. Yeah. And then what, we'll meet here